Good afternoon, everyone, and a warm greeting to our respected guide, Professor Anshuman Kumar. I, Shivam Arora, and it's honor to kick off our group's presentation for PH 530 Light Matter Interaction, titled Enhanced Sensitivity of LIGO Gravitational Wave Detector Using Squeeze State of Light. Our team of six, myself, Ram Sarup, Ramesh, Rahi, Shubhajit, and Ritik, has poured our efforts into this project, exploring how quantum mechanics and light manipulation revolutionize gravitational wave detection. We will guide you through this journey, and I will set the stage by introducing gravitational waves, LIGO's mission, quantum noise challenges, and the foundational physics of squeeze state. Let's start with the cosmic backdrop. Gravitational waves, predicted by Einstein in 1961, are the distortion in space-time caused by massive accelerating objects like merging black holes or neutron stars. The ripples travel at the speed of light, stretching and squeezing space itself. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made history in 2016 by detecting these waves, measuring mirror displacement as small as 10 raised to the power minus 18 meters over its 4-kilometer arms. Push that in its perspective is like detecting a shift 1,000 times smaller than a proton's diameter across a distance from Mumbai to Pune. This precision relies on laser interferometry, which light beam splits, travel down the arm, reflect off the mirror, and recombine to reveal tiny phase shift caused by the gravitational waves. But here's the catch: quantum noise. Light, at its quantum level, has inherent uncertainty that creates noise, limiting LIGO's sensitivity. Think of it as a static drowning out of a faint radio signal. These are the culprits: short noise from random photon arrival at the detector, and the radiation pressure noise from photons jostling the mirrors. These noise sets a sensitivity floor called the standard quantum limit, or SQL. To break through, LIGO uses squeeze state of light, a quantum technique to redistribute this uncertainty. The idea has evolved since 2013, with major leaps in 2019 and 2024, when LIGO suppressed the SQL. My teammates will unpack those milestones, but first, let's understand the physics. In quantum mechanics, light has two quadrature, as we can see that x1 and x2. x1 is related to amplitude in phase quadrature, and x2 is related to phase quadrature phase. The Heisenberg uncertainty principle says uncertainty's product must be at least h cut by 2, where h cut is the reduced Planck constant, and its value is equal to the 1.05 into 10 raised to the power minus 34. In a coherent state, like a laser beam, the uncertainties are equal. That is, delta x1 is equal to delta x2 is equal to root h cut by 2. Here we can see the equation. Look at this uncertainty ellipse. Yeah. So look at this uncertainty ellipse. It's a circle balanced in both directions, representing its minimum uncertainty possible in classical light state. This is what LIGO's laser start with. Now, squeeze state twist this picture. Delta x2 less than root h cut by 2. Delta x2 less than root h cut by 2 and delta x1 greater than root h cut by 2 means phase quadrature is squeezed and amplitude quadrature is anti-squeezed. We can reduce the uncertainty in x2, the phase quadrature below the root h cut by 2, but at the cost of increasing x1, the amplitude quadrature. This is non-classical, something a regular laser can't do. Here, the squeezed vacuum state, the ellipse, flattens along x2, showing less phase uncertainty, while stretching along x1, as we can see in this diagram. For LIGOs, squeezing x2 cut short noise. Those phase fluctuations did blur the gravitational wave, making faint cosmic events clear. It's like tuning a telescope to see dim stars. This is bedrock of our project. Quantum physics meeting astrophysics. I have laid the groundwork and now I will pass to Ram Sarup, who will dive deeper into the squeeze state and the LIGO design challenges. Ram Sarup, over to you.
Hello everyone. Thank you, Shivam. I am Ramswarup Kumawat. I will unpack the quantum mechanics of squeeze state and how they fit into LIGO's design. I will cover it in cell 2 and 3. Expect some equations, diagrams, and physics to bring this to life. Let's start with the squeeze state. As explained, Shivam, that in quantum mechanics, light has two quadrature, amplitude in x1 and phase in x2, governed by the Heisenberg uncertainty principle that are like this, and that uncertainty product of x1 and x2 always greater than s squared by 2. Here delta x1 and delta x2 are uncertainty in the quadrature. In coherent state, like a standard laser, the uncertainty are equal and minimized, both at root s squared by 2. Here is the math. We can see that delta x1 is equal to delta x2 and both are equal in the root s cut by 2. It is a circle of uncertainty in phase space. Uh, we can see it in the next in diagram. It is also discussed by Sion, but is state, that's where it get interesting. That is the most interesting part of this presentation. We reduce uncertainty in one quadrature, say phase x2, below root s cut by 2, while x1 uncertainty grows. So delta x2 decreases and delta x1 increases. But the product of this uncertainty remains constant. as before. This creates an ellipse, not a circle. In LIGO, we squeeze X2 to cut short noise, which depends on phase fluctuation. Now, look at this diagram. It shows three uncertainty ellipses. First, a coherent state with equal speed. Second, a vacuum state. Second is the vacuum state. Same but zero amplitude. And in third, this is a squeeze vacuum state with narrowing X2 and stretch in X1. This squeezing of X2 directly boosts LIGO's ability to detect tiny phase shift from gravitational wave. Now let's connect this to LIGO's design. We can see it in cell 3. LIGO has two sides, Hanford and Livingston, each with 4 km Michelson interferometer. Every cavity in this arm amplify the signal. A gravitational wave changes the arm length delta L and we measure the strain H. H is delta L by L. Uh, It is a dimensionless strain. L is order of 4 km and H is order of 10 raised to the power minus 21. So we can calculate that delta L will be 10 raised to the power minus 18 meter. That's why noise matter too much. Quantum noise source. So there are mainly two type of noise source. First is short noise. Second is radiation pressure noise. Short noise below short noise is high frequency noise. High frequency means above 100 frequency, 100 hertz frequency, and radiation pressure noise is below 100 frequency. Short noise dominant above 100 hertz, scaling with the square root of laser power. Its photon statistics radiation pressure noise below 100 hertz, scale with power and mirror mass. We can see here in the formula. Its momentum peaks. The SQL is where this balance limiting sensitivity without squeezing. So at standard quantum limit, the minimum noise achieved when noise in as short is equal to noise in radiation pressure. So noise spectrum behavior, we can see that uh, at higher frequency, noise short dominated, and this is constant with frequency. And at low frequency, radiation pressure noise prevail, and this is dependent like that. So at a particular frequency, this is 37 hertz, where the short noise and the radiation pressure noise equal. So here we can say that the quantum noise is minimized. Also, we can see it in diagram that short noise is constant with the frequency and radiation pressure noise is decreasing with the frequency at a particular frequency. We can see that both noise are equal and this is 37 hertz. This is SQL frequency. So squeeze state reshape uncertainty to suppress short noise. I direct to CM introduction. I will pass the baton to Ramesh Yadav, who will cover the 2013 breakthrough where this idea first proved its worth. Ramesh, take it away.
Uh, Thank you, Ramguru, for the detailed setup explanation. Hello, everyone. I am Ramesh Yadav, and I am excited to share the 2013 breakthrough with skill states debuted in LIGO's Hands-for Detector X1. Over my 13 minutes, I will cover the key results, the noise reduction model, and how this milestone reshaped the gravitational wave detections. Let us step back to the 2013, 2013 mm, and see the quantum physics in sections. Mm, The LIGO scientific collaborations made waves by injecting a space vacuum state into H1 state into H1 that you can see in the slide here. Here is the squeeze vacuum source which we have ejected. Yes. Now a 2.15 dB reduction in short noise in the 150 to 130 Hertz bands, vital for spotting binary neutron star merger and black hole coalescences. This translates to a 22% drop in noise amplitude and a 28% sensitivity boost. Let us unpack this. Here is the mathematical derivations. Now we are going to understand these mathematical derivations. Noise amplitude reduction is 10 to the power minus 2.15 divided by 20. That is approximately 0.781%. Then multiply by 100. That gives a 22% cut in amplitude, noise amplitude reductions. Sensitivity improves inversely. That is 1 divided by 0.781. That is approximately 1.28, or we can say that the 28% gain. Physically, it's like amplifying the laser power by 64% without the heat distortions. We cannot loss in heat or something else. Why? This is a pretty clever idea. How did this pull off? They use an how did they pull off? They used an optical parametric oscillator, which is normally called as OPO, with a PPKTP crystal pumped at 532 nanometer to generate speed light at 1064 nanometer, a parametric down conversion. Parametric down conversion, which you can say the see in the slide 8, where the parametric down conversion states why speed vacuum still introducing this. Now we are now going more deep in the mathematical part. The pump light drives the crystal, producing a squeezed vacuum state. Mathematically, this is governed by squeezing parameter, which is S, that is equals to e raised to the power r by 2 bracket a square minus a dagger square, where a is a creation operator and a dagger is a annihilation operator, and r is the squeezing parameters. Okay, this is the mathematical derivation, I think, which you have. explained by the Ramsuru. Okay, here is the derivation. Or we can say that this is the graph how they are deep diving into that. Now, the scales x2 by e to the power. Here x2 and x1. One is a phase squeezing and another is a amplitude squeezing. This scales x2, that is amplitude squeezing by e to the power minus gamma factor, and x1 by e to the power gamma factor, which is governed by the uncertainty relations. For 2.15 dB, R is that is approximately 0.25. So that's come out to be e to the power minus 2R, that is approximately 0.61. Now cutting the phase variance x2 square by 39%, which is quite good. That's direct hit on short noise. Here the we only want to the short noise reductions. That's a very good we have achieved by reducing the x2. Now we are going to more on the now we are trying to explain this strain sensitivity and frequency versus frequency curve. Here you can see that the rate which is showing that the when we don't introduce the speech vacuum state, then there is so many noises are coming from the outer space. Now, after introducing the speech vacuum state, here blue lines which are giving the very less noise, which is very good for our detectors. Now we have achieved this blue line in our strain and frequency curve. By help of this, we can analyze the outer space incidences. And here is the proof for H1 is strain sensitivity with squeezing blue lines and radar without squeezing. This band is now another thing which is more similar to this. That is the two line which are showing that the how the squeezing factor reducing the noise. Here on y-axis we have the strain noise amplitude spectral density, and on x-axis we have a frequency. Here without introducing vacuum or speech vacuum states into the detector. Here the red line is showing how much the noise are coming from outer space. But by introducing the speech vacuum state, this blue line depict the how the noise are improved our sensitivity. Now, by improving these much, we have achieved the 28%, which is quite good. Now, I want to hand over this to the Ryan, who will explain the next.
Thank you, Ramesh, for this fantastic overview. Hello, everyone. I am Rahir Yas, and I am here to take us behind the scenes of the 2001-2013 Suki States implementation in LIGO H1. I will detail the technical enhancements, the challenges faced, and the sensitivity gains achieved. Let's explore how this quantum leap happened. First, the upgrades. They swapped heterodyne for homodyne readout, directly measuring the phase quadrature x2. To target short noise, homodyne locks onto phase shifts, amplifying LIGO's gravitational wave signal over noise. Next, cavity power jumped to 40 kilowatt as short noise is inversely proportional to the power. So the more the power, it helps us in uh, decreasing the short noise. Though it nudges radiation pressure noise up as Ramaswamy noted, finally an output mode cleaner or OMC filtered high order optical modes with 82% transmission efficiency. Uh, Finally, it was it filtered approximately 82% transmission efficiency, cleaning up the signal. Think of it as polishing the lens to see sharper stars, but it wasn't smooth. Though we got the optical losses, which were hefty, that were 56%, and total detection efficiency was about 44%. So this total detection efficiency was reduced to 44%, and the total efficiency decreased is decomposed as like due to the factors of mode mismatch, that is 25%, and OMC scatter absorption is 18%, and Faraday isolator cost is approximately 20%, that is mentioned here. These losses diluted the squeezing effect, like pouring water into a leaky bucket. Phase noise at 37 milliradian. This is the phase noise at 37 milliradian. This was minor, degrading squeezing by less than zero point 0.1 decibel. This is the minimal degradation that was due to the phase noise, that was zero point 0.1 decibel. The thing next is the wake scatter mitigation. How we mitigated the wake scatter. So it was handled with a traveling wave OPO and 40 decibel isolation and Faraday isolators. Now let us come to the results and amplifications. The reward was worth it at 2.15 decibel short noise reduction. That was considerable reduction in the short noise. That is like equivalent to 65, that's equivalent to 64% increase in the laser power without thermal distortions. The noise spectrum total total noise, short noise, and radiation pressure noise with the SQL at 37 Hz with sequencing short noise dips enhancing the 150 to 300 Hz band. Key for binary neutron star coalescence. The signal to noise ratio for BNS and spiral signal scale is as given in the equation that is here. This boosted detection rates linking gravitational waves to multi-messenger astronomy, like pairing them with light from neutron star collisions. That was the 2013 triumph. Now I will hand over to Subhajit. That's our next presenter who will take further us to the 2019 O3 run and 2024 Leave Beyond the SQ.
Hello, I'm Subhajit Mondal and I'm going to talk about the O3 run in 2019. So it was reported in the physical review letters where squeezing became operational in advanced LIGO. So in the O3 run, they have used the squeezing and below is the key results found from the O3 run. So in the Livingston detector L1, nominal squeezing level was 2.7 decibel and
maximum squeezing level was 3.2 decibel. So the binary neutron star range boosted from 123 megaparsec to 140 megaparsec, increase of 14%, and the detection rate was also increased by 50%. In case of the Hanford detector H1, squeezing level was 2 decibel. Binary neutron star range was boosted from 107 megaparsec to 120 megaparsec, and detection rate it also increased by 40%. So uh, before this O3 run, they were not able to detect a lot of uh, neutron star mergers binary because their frequency were a lot lesser and noise would have dominated them. So after this discovery and implementation, they were able to detect some of the other binary neutron star mergers. One of them is the GW 190425, which was detected by the squeezing enhanced L1 detector. Below is the graph of L1 strain noise versus the frequency. So as we can see, uh, so the black one is the reference without squeezing. The purple is the quantum noise model without squeezing. Green is the quantum enhanced sensitivity, and the gray one is the sum of non-quantum noises. So here, as we can see that after uh, around 100 hertz, there is a visible difference in the without squeezing reference and the quantum enhanced sensitivity. So what happens is that there are few peaks like this year around 150 hertz, which could not have been observed without the squeezing of quantum light, but it can be observed after introducing this squeezing. So one of them is the GW 190425. That is how it is improving our detection rate and also the range. So let's come to the next thing, that is the how they had done it. So they have used uh, so there are some O3 technical advances. So they have used in vacuum optical parametric oscillator. They basically installed the optical parametric oscillator in the uh, antisymmetric arm so that they reduce the backscatter and they suppress the backscattering. And they have achieved isolation of 130 decibel via bow tie cavity geometry and Faraday isolators on suspended optics. What it has impacted? So it has impacted that it has eliminated the noise from stray light coupling into the interferometer. So it has just increased the efficiency, mm, and also decreased the loss. So how much it has increased the efficiency? So uh, in 2013, the efficiency was to 44%. It has increased to 75%, and the loss has decreased to 25%, which was 56% in 2013. So if we break down the loss, then it can broken down in three parts. Faraday isolators output, mode cleaner, and mode matching. Together with them, we achieve this much of results improvements. If we come to the non-linear gain, so it is defined by the pump power by the threshold power. Threshold power is the OPO threshold power. So in case of the Livingston L1, this nonlinear gain is basically 2.7 plus minus 0.1. yielding 2.7 decibel of squeezing. In case of the Hanford one, H1, the G is 2.3 plus minus 0.1, yielding squeezing of 2.0 decibel. And if we come to the phase noise, it is reduced to the residual noise is reduced to 15 milliradian, which was 37 milliradian 2013. So its impact is negligible for less than equal to 3 decibel squeezing. That's it. So I will conclude my talk here and give it to Itik, who is the next talker.
Hi everyone, myself Ritik Verma. First, I would like to thank Shubhajit for his detailed talk in the Q3 run. So we can see that by doing several uh, kinds of modification in the Q3 launch, we have achieved some sort of better decision of measuring the gravitational waves, but still it was not uh, large enough for the better detection. And after that, the fourth LIGO run, Q4 was uh, committed, which surpasses the standard quantum limit SQL. So basically, standard quantum limit SQL is the competition between the two noises. First is the vacuum noise, and the second is the radiation noise. So for this, we have the key components like 300-meter filter cavity. In this filter cavity, so it rotates the squeeze angle phi of omega to align with the interferometer's optomechanical coupling. So this relation basically said that how the optomechanical coupling and the squeezing angle relates together, and there are several quantities on which they basically depends, where the omega naught is defined as 2 pi c by lambda, and this is also called the laser frequency. Next is the p arm, where p arm is nothing but the power of the arm cavity, which is about 100 kilowatt. And due to these reasons, this enables frequency dependent noise uh, suppression. So by doing this 300-meter filter cavity, we get two more most important results. So first is the 3 decibel below SQL, which have a factor of root 2 in amplitude at about 35 to 75 hertz. So this range of frequency is very important for the detection of uh, uh, one of the most important astronomical objects like binary and neutron star mergers. So basically, this range is very special. So why this is special is that, see, the neutron stars and black holes mergers can emit gamma radiation in various range of frequency, but to get all the other informations, we need to measure this in the lower frequency limit. And the second most important results we get by doing this filter cavity is that 5.6 decibel short noise reduction at kilohertz frequencies. And this frequency is basically related to the ne- ne- neutron star and post-merger studies, which we can observe after the merging. Now, the standard quantum limit strain noise, which is given by the HF, is basically related to the frequency and mass of the mirror, which is given by H equal to root over 8 H cut by M 2 pi F square by L square, where the mirror mass is about 40 kg and length of the arm is about 4 kilometer. Now, at the standard quantum limit, we get the frequency as 37 hertz. and we get the factor H as 1.8 into 10 raised to power minus 24 Hertz of power minus 1 by 2. Now, it has several implications. So, two of the most crucial are the lower frequency boost, which basically means the sensitivity of improvement for the binary black hole mergers, which has the frequency limit of 30 to 100 Hz. And the second is the high frequency gain, which is basically this enables the detection of neutron star and post-merger oscillations, which reduces the gamma radiation at the frequencies which is larger than the 1 kHz. Uh, so this is the graph we can see for the strain amplitude spectral density and the between frequency. Now from this graph we can see that by doing these all implications and modification, the noise is reduced below 3 decibel, which is very good and we can properly detect. But still we have many other things which we have to rectify for the better detection of gravitational waves. Now let's move on to the frequency dependent squeezing and the mechanism and results. So the mechanical coupling k omega and the squeezing angle phi dependence phi omega equal to tan inverse k. And by doing this, we get this result, which is given as h equal to 8 h cut by m 2 pi omega square L square, where uh, the smaller is the squeezing parameter and omega is just the frequency. So what is the result of this? We get most important result as the broadband noise suppression. We get squeezing and reduces this quantum noise across all the frequencies. For example, below 3 decibel SGL at omega, which ranges from 35 to 75 Hertz. This also has some limitation. One of is the filter cavity mismatch, in which the cavity line width, which is given as 42 Hertz, is mismatched with the standard quantum limit frequency 37 Hertz. And due to this mismatch, that limits the low frequency performance. Now let's move on to the most one of the crucial things, the astrophysical impact. So there are three portion of this. The first is 550 to 300 Hertz band, which is uh, critical for DNS in spirals where the SNR scales as f power minus 7 by 3, which is very small, and that's very good for us. The band contains the merger strongest emission before coalescence critical and for measuring the total deformability delta. And that's why we need to measure in the very low frequencies so that we can get all the other information about these black hole markers. Second is the O4 gain, which is better for sky localization and TDL deformability studies. And third is the future upgrade. So which is given by the 6 decibel broadband reduction. So this approach targets the quantum noise suppression across all the frequency using frequency dependent squeezing FDS, which was formula is basically given as h quantum equal to h quantum exponential of minus r f, which where RF is the frequency dependent squeezing parameter, and that basically is a function of frequency. Now, by launching the O4 LIGO, we still have various challenges in the future directions. So there are three things. The first is the current losses. So losses of 10 to 25% phase noise filter cavity mismatch are still there. Second is the next step. So next step is to reduce the losses, optimize FDS, and increase the nonlinear gain. So by doing all these things, we are actually reduces the noise parameter, and we can get the better detection for the gravitational waves. And the second is the vision. Cosmic Explorer and Einstein telescope with advanced squeezing for deeper cosmic insight. So this is the whole story of the our O4 launch, which is still our one of the um, modern LIGO detector we still have, but yeah, we still need some of the modification to improve the sensitivity of measurement. So the squeeze state of light have significantly enhanced the LIGO's sensitivity through three key milestones, which are in the first. Our first milestone comes at 2013, where the squeezing in LIGO achieved a 2.15 decibel short noise reduction, which is 28% improvement from the previous one, which validates the squeeze vacuum injection in a full-scale gravitational wave detector. And we get a noise reduction of about 0.61. The next key milestone comes at 2019. So we get, since our the third generation run, which is O3, we achieved 2.7 decibel squeezing at L1 and 2 decibel at H1, which rises the binary neutron star BNS detection rates by 50% at L1 and 40% at H1. So the next large milestone comes at 2024 latest, which is the FDS, which is frequency dependent squeezing, and that suppresses the standard quantum limit SQL by 3 decibel at 35 to 75 hertz, which basically enhance our sensitivity across all the gravitational wave frequencies, and we can define the gravitational SQL strain equation as HF equal to H cut divided by M 2 pi F squared L square, where F is the frequency and the length capital L is the length of the arc. So this fusion of quantum optics and astrophysics has expanded our ability to detect phenomena like binary black holes and mergers and neutron star collision. But still, we have to measure at the very low frequency. Since if we don't measure at very low frequency, then all the information about the radiation emitted by the black hole mergers and neutron star will go away. So this is our presentation. Now, after that, I would like to thank my teammates, uh, Shivam, uh, Shubhajit, Ramesh, Rahi, uh, and myself, and Ram Swarup, and also to our guide, Anshuman sir. Thank you.